Okay, so we concluded our last session with discussion about this heartbleed attack. So, any question related to what we discussed in the last class? Okay, no questions. And any question related to what we discussed related, any query related to the assignment because the assignment deadline is today. Uh, yes, some of you might be using those extra days, but at least the deadline is today. So I was wondering if you have any questions related to the assignment. Everyone is doing fine. Okay, good. Uh, so, uh, um, so although we had a few things left related to TLS, um, I titled this lecture as Secure Cell because there were only two, three things that I wanted to talk about TLS in this lecture. Okay, so the first thing that I want to talk about TLS is a very relevant attack that is possible in TLS, and people have shown that to be working on different versions of TLS. So this is something which is called a version downgrade attack. Okay, so basically we looked into the history of SSL and TLS, and you have seen that SSL started back in 90s, and then different versions kept coming, and TLS 1.3 is the most recent one. And of course, these who has not muted Harshit. Okay, so yes, so of course these different versions were um, developed because the previous version had some issue and many of the times some security flaw. Um, so what an attacker could do is that, and we discussed that during the handshake, two entities start to communicate in plain text, and then they agree on the version of TLS that they will utilize during their communication and the crypto and the corresponding cryptographic algorithms. So the crypto suit. So therefore, so a very typical attack that is possible is what is called the version downgrade attack. So although in the current time everyone should be using TLS 1.3, but of course over the internet not everyone is so updated, and therefore there are some servers which have this facility to allow the clients to use the previous versions as well. So these days it is not very uncommon to have TLS 1.2. But if you go below that TLS 1.1 or even the SSL 3.0 versions, then what happens is that you could utilize a very insecure version of the cryptographic protocol. And if that insecure version is utilized, then the attacker will have an opportunity to break the authentication and encryption crypto algorithms in that protocol. So for instance, if so MD5 is a very old hash function, um, but it has been shown that MD5 could be easily broken these days. But MD5 is part of the previous versions of TLS, and if the client could make the server agree to utilize MD5 for hashing messages, then the client, which could be an attacker, has an opportunity to forge messages. Okay, so I hope this idea of version downgrade attack is very clear. And similar, you could see some of these papers and you will know what specific details were utilized in this version downgrade attack. Okay. Any question related to this version downgrade attack? Okay.
Sir, in Postgres database, there is some MD5 encryption being used. So is that unsafe?
Yes. So MD5 is so what happens is that this MD5 function has a very short output. Okay, so the output length is very short. So yeah, so you have not done any assignment, and I have not discussed this as well, but hopefully when you probably discuss, if we have an opportunity of discussing blockchains, we will discuss that. So every hash function has a certain output length. Okay, so that could be 512 bits or 256 bits, and the um, cryptographic strength that the hash function provides is dependent on the length of that output, so the hash output. So you could think of it as these random bits. So let's say if you have 256 random bits, and if you have only 32 random bits, and so if an attacker has to somehow guess those 32 random bits coming out of a hash function, it is easier for an attacker than to guess those 256 random bits that is coming out of the hash function, or pseudo random bits that is coming out of the hash function. And therefore, if the length of the output of a hash function is small, then it is easier for the attacker to break the, let's say it is utilizing digital signature, so then break the digital signature. So this MD5 algorithm has a limitation on the largest number of bit that the output could have, and therefore this is not very secure hash algorithm in these days. So probably 10 years ago it might have been all right, but these days it is not. So let me just quickly show you that in TLS 1.3, MD5 has been dropped because of this region. So you see that I have been asking you to use SHA-3. So SHA-3 is considered a secure hash algorithm. So SHA-2 is also fine these days. It has not been if you use 256 bits as output, it is also doing fine. But if you want to have a system which is going to be in place for next 5-10 years, then you should definitely think about using SHA-3 as the hash function. Okay, so yeah, so MD5 has been dropped in TLS 1.3. SHA-224 is also something which has been dropped in this TLS 1.3. Non-AEAD ciphers. So there are, we talked about it, that what is authenticated encryption, and associated data just means that there will be some data which will be authenticated but not encrypted. Okay, so that is what it means by associated data. The ciphers which do not facilitate authenticated encryption, so both authentication and encryption, they have been dropped, because in many cases you want both authentication and encryption, and we have seen that in TLS we utilize both authentication and encryption. And then if you are using elliptic curve based cryptography, then this area has also has received a lot of attention, and it depends on the curve that you choose. So you might have utilized one elliptic curve for the assignment that I have given you. So any curve is fine, which is provided in the libraries that are there. But over the years, people have found that if you utilize a certain curve, the security may be lesser, and therefore over the time better curves have been designed, and the previous older curves have been dropped, and that is what has happened in TLS 1.3 as well. And some new and faster algorithms have also been added. So ChaCha 20 is a new stream cipher, which is actually touted as the cipher which will replace many of the RC4 or the next version RC5 stream ciphers, and then some new message authentication code algorithms, some digital signature algorithms, and some key exchange algorithms. So they have been added as well. Okay. Okay, so one thing that I also wanted to talk about is this forward secrecy. Okay, so this is the perfect forward secrecy. So this is a term which you will hear in many systems these days. So I wanted to talk about it. But before that, I also want to talk about this ECDH key agreement protocol. Okay, so we have already talked about Diffie-Hellman key agreement protocol. Okay, so the first version of Diffie-Hellman key agreement protocol that we talked about, we said that this works and it makes sure that both the sender and the receiver have a secret key which is the same at both ends. So that was the first version of digital Diffie-Hellman key exchange. But then we said that it is because we are not authenticating the parameters that are being communicated, therefore it is insecure. And then we said that you have to use digital signatures, okay, in order to authenticate the Diffie-Hellman key exchange. And you are also using a digital signature in your assignment, so you know what how those digital signatures could be generated. So you could use RSA for generating digital signature. But now you also know that you could use elliptic curve cryptography for that. And if you have already done the assignment, you know that elliptic curve cryptography has many advantages. So faster computation, lower communication overhead, smaller key size. Okay, so it has multiple advantages. And therefore, even this Diffie-Hellman key exchange protocol, people have looked into it and discovered how it could be done on elliptic curves. So which means that you generate those parameters that are generated in Diffie-Hellman key exchange on elliptic curves, and then you generate digital signatures using elliptic curve cryptography, and therefore this whole Diffie-Hellman key exchange protocol becomes much more lightweight. And that new elliptic curve based Diffie-Hellman key exchange protocol is called ECDH, elliptic curve based Diffie-Hellman key exchange. Okay, so this is also something that you will see in more recent crypto algorithms, one of the options in more recent type crypto algorithms. Okay, so yeah, so this is the discussion about the different crypto algorithms. Any question related to these different crypto algorithms? Okay, so let me just talk a little bit about this perfect forward secrecy. Okay, so let me first ask you some quick question. Okay, so let's say you have a sender and you have a receiver, and then they share a secret key K, and then they start communicating messages. Let's say they had this secret key K, and they started using secret key K on January 1st. And on January 20th or so, this secret key was somehow compromised. Okay, so in the middle of January sometime, this secret key was compromised. The attacker was able to somehow crack this secret key and find that secret key. So then, do you think that the previous messages that has been communicated between sender and receiver, they could also be decrypted by the attacker, or they could not be decrypted by the attacker? So before the key was compromised, so those messages could be decrypted by the attacker or could not be decrypted by the attacker. This is a very easy question, so somebody should reply.
Can you repeat the question?
So the secret key K is being utilized by sender and receiver, and let's say it started on January 1, they started exchanging messages, and sometime in the middle of January, this secret key got compromised, which means that the attacker got access to the secret key. So now the question is that all the messages that have been communicated between January 1st and let's say middle of January, those messages, can they be decrypted by the attacker or not?
Yes, sir.
Sir,
They can be.
Sir,
Yes.
if nonce is used, it may not be decryptable.
No, so nonce is something that you also share in plain text. So it is not something that you could just randomly encrypt a nonce and send it to the um, receiver, and the receiver may make sense of that nonce. So that is also, there has to be some deterministic way of generating those nonces as well. So it is not that just adding a nonce will provide you any security. So the security is always provided by some secret, which is shared only between the sender and the receiver. Without a secret, there is no security. So nonce could be randomly generated, or there must be a pseudo-random function which will generate these nonce. But there is always a deterministic way of generating these nonces. Okay. Yes, so that is correct, that all these messages will also be decrypted by the attacker because the attacker has access to the key. Okay, so then the solution that, so this is problematic because in many systems it is always possible that after a time the secret key that you are using could get compromised. Because of certain mistake by either the sender or the receiver. But if because of that compromise, all the previous communication can also be decrypted, then that becomes more problematic because now you know that you made one mistake and then you do not have any security at all, no matter when you started utilizing a very secure protocol. Okay, so that is a very problematic scenario. And therefore, people came up with this concept of forward secrecy, which means that if you lose, so you come up with a way of generating secret keys, which are called ephemeral keys, and which are utilized for a very small time frame, and that is why they are called ephemeral. So the keys will be utilized for a very small time and then they will be refreshed. Okay, so and how will you refresh? So there are many different mechanisms of refreshing the keys, and one typical mechanism will be that you just go ahead and utilize again the ECTH key agreement protocol to generate new keys. Okay, so that is one way, but that is very computationally expensive mechanism of renewing keys, but that is very very straightforward way of renewing keys. Okay, so this means that if at a certain time, so let's say you utilize a secret key for just one day, okay, and then you renew the secret key. So on January 1st, you might have utilized one secret key. Then on January 2nd, you might have utilized another secret key. And then on January 3rd, you might have utilized third secret key. So that is how you just went on utilizing these different secret keys. So even on, let's say January 20th or so, you utilize the secret key, and on that day, sender or the receiver made a mistake, and the secret key utilized on January 20th got revealed to the attacker. So then all the communication that you made before that is something that is not compromised, because the secret key on January 19th was different than the secret key on January 20th. So even though the attacker could get hold of the secret key that is utilized on January 20th, it cannot do anything about the previous communication. So your previous communication remains secure. And this is also important to note that even though that secret key gets compromised, there is still you can always go ahead and launch this ECDH key agreement protocol again, and then you can generate new secret keys to have secure communication on January 21st and so on. So that is also a possibility. So this is, I guess, the very informal definition of forward secrecy, that even though, so after the compromise of a current key, all your previous communication still remains secure. Okay, so is that clear to everyone? Okay. Okay, so I already spent some time there. So here I just want to mention one thing. So I started with that motivation that you may have, you may be using a platform, an insecure platform, and then you might be in a hostile country utilizing probably a browser, a Wi-Fi access point, which may also be compromisable by an attacker. So even in those scenarios, it is possible that you could securely access your email and securely send or securely access some particular website. And that has been possible because of TLS. So that was the motivation to introduce TLS. And therefore, if you think about one of the most important application of TLS, so HTTP over SSL or TLS is the most important application of TLS. And so you see that the proxy or some other version, it might be the attacker which may have control over that. The internet is something where the attacker is very active, but even then you will be able to securely access HTTP server from your browser through this HTTPS tunnel, or which is just a security tunnel where you could send secure messages and receive secure messages. Okay, so HTTPS just provides end-to-end secure protocol for hypertext transfer protocol HTTP. And then the properties that are provided by TLS. So we already have discussed that: encryption, authentication, and integrity protection as well, integrity of the messages. And then we also talked about this, that authentication is, if you are surfing a website, typically it is only the server which is authenticating to the client. Okay, so the client is typically not authenticating. So there may be different other mechanisms utilized by the server to authenticate the client. And one of the mechanism will be to have a username and password based authentication. But that is different. This is not part of TLS. Okay, so that is the only thing that I want to talk about HTTPS. Any quick question about HTTPS? Okay. Okay, so now we go to another transport layer security protocol, which is called Secure Cell. And it is again something which is very, very popular, and most often it is utilized to do secure logging. So I showed you an example of my GitHub account where I had created these keys, and then I had shared the public key with the GitHub, my public key with the GitHub account, and then I was able to push my code very easily. So that is one example of utilizing these SSH protocol. And so, but in most cases, if you are accessing, let's say, any server at IIT Delhi, if you are at home, you utilize SSH. So for instance, if I have to update my website by accessing ITD server, I utilize SSH. So yeah, so there could be many different usage of SSH, but remote login is something which is the very popular one. Okay, and of course this is happening on an insecure network. So there are commercial versions of SSH also available, so the paid versions, and there are, of course, many of us use the OpenSSH, which is the free version of generating these SSH keys. Okay, so SSH sits over TCP IP, and SSH consists of these three different protocols, or you can say sub protocols. Okay, so the first one is the protocol which actually provides the security properties that are required there. So authentication, so server authentication. So when the client is accessing a server, so the server is authenticating to the client of its identity. So server authentication, and then confidentiality using encryption, and then integrity of the messages. Okay, and it can also provide compression that is just optional. And then on top of it, so once you have this SSH transport layer protocol, which can provide all these properties, then there are two other protocols which will be run over it. So the user authentication protocol. So now we have a specific way in which the client could also be authenticated. Okay, so if the server wants to authenticate the client, now there is a specific way in SSH that it could do it. And that is what is the SSH user authentication protocol does. So the client side authentication. And then you have a connection protocol, which is actually, so you have these, so you see that we have encryption and authentication in the SSH transport layer protocol for our messages. So what this connection protocol does is it establishes a connection, and what it does is it multiplexes different streams of encrypted and authenticated text over different channels. So you have different logical channels, and you have different keys that are being utilized, and therefore you have different sets of encrypted and authenticated messages. And what it does is it just multiplexes all of them in order to have this connection protocol, which is part of the SSH. So SSH first builds upon this transport layer protocol. So that is the fundamental encryption and authentication mechanism. And then it has these two other parts where it has the facility of doing authentication on the client side, and then multiplexing multiple logical connections. Okay, so that is our stack. And now I will go through each of these three in a little bit more detail. But yeah, at the high level, is this stack clear to everyone? So what is happening in the SSH? Because we have discussed TLS, and if you have understood TLS, things will be very similar here. It's just that I want to highlight a few differences, but very similar things are going to happen here. Okay. Okay, so the first is the transport layer protocol. So I talked about it. Of course, the functionalities I also talked about: encryption, server authentication, integrity protection, and compression. So like TLS, we must have a key exchange protocol. It could be a Diffie-Hellman key exchange protocol or some other key exchange protocol. It must have a public key based algorithm, so public key based encryption and digital signature algorithms. It must have signature symmetric key based signature encryption algorithm, symmetric key based message authentication code generation algorithm, and it should also have a hash algorithm. So during the handshake, all of these algorithms are agreed upon between the client and the sender. So this is again very similar. Now I also like to show you a typical message exchange that can happen between a client and the server. So what initially happens is that the client and the server will establish a TCP connection. So that is something. So that is the first step here when considering SSH protocol, and then they will start to do the handshake. Okay, so we have talked about the handshake. So agreement on what type of crypto suite or what type of crypto algorithms will be utilized in this connection. Okay, so SSH protocol version, software version, very similar to what happens in TLS. And then once the algorithm negotiation is completed, then you go ahead and the client and the server go ahead and do a key exchange. Okay, so very similar. So why is the key exchange needed? So they may have a private key, public key, but what is the meaning of the key exchange? What will be the output at the end of the key exchange? So can somebody tell me what will be the output of that key exchange algorithm, or what will happen at the end of the key exchange algorithm? So can somebody just quickly tell me?
Both will have same some secret shared with them, secret key.
Yes, so both will have a secret key that they might have either derived or they might have shared. So one of them might have shared with the other one. So secret key means symmetric key. And then so there are some end of key exchange messages to validate that the key exchange has successfully completed. And then you can start utilizing that secret key or symmetric key to start encrypting and authenticating the data. Okay, good. So now what happens in that last part? So when you have a message and now you want to encrypt and authenticate data. So here there is significant difference between what happens in TLS and what happens here. So so remember earlier discussing while discussing authenticated encryption, I had said that SSH utilizes encrypt and MAC algorithm. Okay, so this is what we will see here, that so once you have a payload, okay, so you could compress. More often you would like to compress the payload before encrypting it. And so once you have the compressed load, then there will be some other things that you might need to add. So for instance, you might need to add some padding, you might need to add what is the packet length. So these kind of header information, some sequence number that you would like to add to that particular packet. And then what you will do is you will call both functions, so encryption algorithm and the MAC generation algorithm. So on the message here, so if this is the message, you call okay, so this is so you have this part which is fed to the encryption algorithm. So now you have this ciphertext which contains so this ciphertext actually is the encrypted version of this packet length, padding, compressed payload, and some additional padding that might be required. And then this MAC, it along with this part of the message, it is also trying to authenticate the sequence number. So you don't want to authenticate the sequence number, and so you just you don't want to encrypt the sequence number. So therefore, it is not part of the message that is being fed to the encryption algorithm. But of course, you want to authenticate the sequence number. So that is also fed to the message authentication code generation algorithm. And then you have this authentication type. So you are doing both encryption and authentication of the message here, and then you are sending that over. And therefore, this way of doing authenticated encryption is called encrypt and authenticate. Okay, so any question related to what is happening here? Okay, okay. So I said that we would not like to encrypt the sequence number. So can somebody tell me why it should not be encrypted? So the sequence number, but it should be authenticated, of course. So why should it not be encrypted, but it should be authenticated? Any guess about a possible answer?
Sequence number is basically out of delivery message. If they are coming, the outer protocol is basically using the sequence number. It will decrypt after definitely it will not encrypt sequence number because it is part of something outer protocol to see the flow of the packets.
Okay. Anyone else would like to add something?
Sequence number don't provide any actual information regarding the message getting transferred. So, so there is no need of having this overweight of encrypting it.
I think the reason why we need authentication is that if someone changed it, and then it can mess up the whole packet.
That's also correct. Good.
So transport layer will utilize this sequence number.
Very nice. Yes, good. So very nice answers. So in fact, all of them were correct, and everyone added something to the other answer. So these sequence numbers must be authenticated, because if you have if somebody could play with it, change it without being detected at the receiver, then the messages will not be concatenated in the right form, and therefore it will be a problem. So it has to be authenticated, but there is no need to do authentication using in the SSH. So at this in the SSH protocol, there is no need to encrypt it because it could be utilized by upper layers to process the packets in a certain order. And then it is also possible that this packet could be encrypted at other layers. Not at this layer, but this might be encrypted at the other layers where it could be utilized. Okay, so this is also one example of authenticated encryption with associated data. Okay, so you see that there is some part of the data which is not being encrypted, but which is being authenticated. So it is just the header information that I said, that there could be some header information that will need authentication but not encryption. And this is one example of authenticated encryption with associated data. Okay, good. Okay, so one more quick question before I end this discussion. So you see that before feeding it to the this encryption block, there is some padding that is being done. So can someone tell me why do we need padding before feeding it to the encryption block?
Sir, to make it some even number of bytes or like multiple of 128 bits or something.
Yeah. Anyone would like to add to it?
To make it suitable for the encrypt block, like block size, make it equal to that.
Yes, so that is a more generic answer. So whatever block cipher that is being utilized in that encryption block or encryption algorithm, so you have to make sure that the input is equal to the block size, and therefore after you do the compression of the data, you do not know what will be the size of the compressed payload, and therefore you will need to add corresponding number of bits to make it equal to the block size. So if we are using AES 128, then you have to make sure that this is multiple of 128. Okay, so yes, so that's the goal of padding. Yes.
That means counter mode is not used in protocols.
Yes. Yes. So there, it is possible to not utilize padding in the counter mode, but so remember this SSH has been developed very long time ago, and people have been using it. So there also needs to be some backward compatibility when you have these different possibilities of using different algorithms in the crypto suite. So the client and the server, if they utilize these different modes where such padding is needed, then you have to have that facility as part of the protocol.
Right, sir. Sir, I was just wondering that whether any of the protocols use AES counter mode or none of the protocols use AES.
So if any of the protocols utilize the AES counter mode, yeah, AES counter mode is very popular. So so in fact, I have what I've told you is to implement as part of your assignment is GCM, AES GCM, and which is in fact a combination of the counter mode with um, some way of creating a digest to create the message authentication code. So which is called GHAS. So without going into a lot of details, so counter mode plus GHAS is the GCM mode. So even though you do not see counter mode directly, it is possible that you will see this counter mode in its benign form, the way we discussed in some scenarios, but you will see counter mode in other forms in many different scenarios, because the counter mode is very versatile. We talked about the advantages of using counter mode, and you will see that it is very commonly utilized, not directly, but probably as sub algorithm of a larger algorithms. For instance, GCM mode that I have already told you that utilizes the counter mode.
Right, sir. Thank you, sir.
Sir,
Yes.
from the diagram, sir, on the receiver side, the receiver can't authenticate the ciphertext directly. Means he will first have to decrypt the ciphertext, and then he can check the authentication.
Yes, that is correct. So that is what happens. So when you have encrypt and MAC approach, so you are actually doing that. So you have to decrypt, and then you have the associated data, which was not encrypted. So you have that data, and then you have the decrypted data, and then you concatenate them, and then you feed it back to the MAC verification algorithm, and then you see whether the MAC is verified or not. So yes, you have to do that. So you see that advantage of encrypt then MAC approach is that you could first verify the validity of the ciphertext, and if that is valid, then you go ahead and decrypt it. So encrypt then MAC. So the first one that I said, which is utilized in IPsec, but not in TLS or not in SSH. So in TLS and SSH, that mode is not utilized, but Yeah, so but it is all right. So at least they are secure. They may not be the most efficient way of combining encryption and authentication, but they have been shown to be secure if you use the algorithms which have been allocated for encryption and the algorithms which have been allocated for authentication in SSH. Okay. Any other question? Okay. So let's have some brief discussion about the other two protocols. Okay, so I said that there are three sub protocols as part of the SSH. One was the transport layer protocol, which I discussed, which basically deals with this encryption and authentication of the data and authentication of the server. And I also said that there is another protocol which involves user authentication, which means that now we are talking about the client side authentication. Okay, so it utilizes, of course, the transport layer protocol, which means it is dependent on the encryption authentication that is already happening as part of SSH. So now if you want to do the user authentication or client authentication, so there are three ways. One is the public key based. So there you share a public key, and then your public key will be verified by the server. Then password based or secret key based, which means that there is a secret key that the server knows that you will be using this server key, secret key, and then the next time you utilize that secret key, the server will be able to verify that. And then host based, which means that it is not just the client, but so client means, let's say, the web browser based authentication. So these two could be the web browser based authentication. But now you can do it host based, which means the platform based authentication. So the platform on which that application or web browser is running, that host could have a public key, or that host could have a secret key that could be utilized to do authentication as well. So these are different ways of doing client authentication, and one or more of them could be utilized. Okay, so of course, password based authentication is dependent on public key based authentication. So it is not that if you have shared, so you have to use that password based authentication alongside an asymmetric key based authentication. You cannot just go ahead and directly utilize the symmetric key based authentication. Okay, so that is some brief discussion about the client side authentication. Any quick question about that?
Sir, host based means IP address verification and all.
IP address, I don't know if IP address verification is part of this protocol or not. So host based means the host may have some secret keys, and those secret key could be utilized to do authentication, or the host will have a public key, and that will be utilized to do the authentication. So rather than that client having a public key and then and the public key private key pair and then doing the authentication, the host's public key private key will be utilized to do the authentication. So that is just the difference here. Okay. Okay, so now we talked about this third protocol, so multiplexing of multiple logical connections, and again it runs over that SSH TLS SSH transport layer protocol. So it could so because of this protocol or sub protocol of SSH, you can have interactive login sessions, remote execution of commands, and then there is something called port forwarding. You can read about it more. So you can read about this port forwarding in the book as well. And so these are some of the things that are provided by the connection protocol, and it is executed after the establishment of an authenticated connection. So SSH transport layer protocol has already been successful, and there are logical connections already in place. And then this protocol will allow for all of them to be multiplexed and work together. Okay, so basically how it proceeds, it will just open a channel, and then you will utilize that channel to do the data transfer, utilizing the encryption and authentication mechanism that we have already talked about. And then once the communication has ended, you will close the connection. So this is a very, you can say, a wrapper type of protocol, which wraps around the original SSH transport layer protocol to establish these parallel or different multiplexed login sessions. Okay, so that is the end of our discussion about SSH. So the next class will be related to wireless security. So if you have any question related to TLS, HTTPS, or SSH, please feel free to tell me. Okay. No questions? Okay, so then I guess then we could end our session today. I will meet you tomorrow, and we will talk about wireless security then. Okay, bye-bye.
Sir.